Okay, so we can get started. Uh, so it's a great pleasure to have with us Professor Thomas Schaefer for our Institute 68th year colloquium series. He is today's distinguished speaker. Just to introduce him, so Professor Thomas Schaefer did his PhD from University of Regensburg, and after that he was a postdoctoral scholar at Stony Brook and at the Institute of Nuclear Theory at INT Seattle, and then at IAS Princeton. And after that, he got his first, he joined as assistant professor at Stony Brook University. And then he moved on to North Carolina State University, where he is a professor now. And Professor Thomas Schaefer has done several excellent works, some of which we learned the subject from him. Like, for example, his reviews on QCD instantons is one of the landmarks in our areas. So I personally learned this subject from his works. He also did a lot of works in finite density QCD, in color superconducting matter, understanding the properties of QCD matter using instantons. And recently he has been also, for many years, he has been also interested in looking at the similarities of the cold Fermi gas and the physics of quark-gluon plasma, and especially the unitary, the Fermi gas near unitarity. And he has excellent papers on estimating the properties like bulk viscosity and several other properties of the cold Fermi gas. And he is recently interested in understanding the dynamics of the critical point in QCD. And he has a lot of interesting paper in the recent years, also a review from earlier. And he will tell us more about this subject, so fluctuations and the QCD critical point. So Thomas, please.
Well, thank you so much for having me, and I'm very sorry that I'm not able to be there in person. I've been to India several times, but I've never been to Chennai. So I certainly hope to visit in the future. So I'm coming to you from Raleigh in North Carolina. It's about 8 o'clock in the morning here. It's still pretty early. And so Raleigh, probably like Chennai, actually does get pretty hot in the summer. So we're in the American South. So it's sort of 80s and 90s right now. So Raleigh is roughly in the center of the state. We're about 2 hours from the ocean and about 2 hours from the mountains. So this is meant to be a kind of general colloquium style talk. And I hope this is appropriate for the occasion. And if you want to know either more details or maybe more basic things, I'm happy to stay on the line after the talk and answer additional questions. So what you see on these images, by the way, the image on the left is something that many of you have probably seen before. It's an event display from the star detector at Brookhaven. And so that shows many, many particle tracks in a nuclear collision. The image on the right is just ordinary vapor, water vapor in the vicinity of the critical endpoint of the liquid gas phase transition in water. And so this milky appearance is what is called critical opalescence. And so roughly speaking, what we're trying to do here is see the kind of phenomenon you see on the image on the right, to see that in the images on the left. So to look for truly critical behavior in the QCD phase transition. So this too is an image you may have seen before. It's a rough sketch, not really a plot with accurate numbers, a rough sketch of the QCD phase diagram. So the QCD phase diagram is in principle controlled by a very simple Lagrangian, which is the one written here in the top in the little box. So this is a Lagrangian that describes the interactions of quarks and gluons, that encodes everything about the strong interaction, the masses of hadrons, the binding energies of nuclei, but it also encodes the QCD phase diagram. So it encodes the ground state of hadronic matter as a function of temperature, which is on the vertical, and the net baryon density of the system, which is on the horizontal. So one landmark that we have is, so we live at very low temperatures on the scale of QCD, and in that limit, the ground state at finite baryon density is protons and neutrons that are bound into ordinary nuclei. And this is really the only point about which we have very accurate information. We believe that as the system is heated, hadrons eventually melt, decompose into quarks and gluons, and that these quarks and gluons eventually form a quark-gluon plasma. And I'll explain in a little bit why we think that this is just a smooth crossover, but a very rapid transition nevertheless. And if you take ordinary nuclei and you compress, you get to dense cold matter, and that is the sort of material that is in the interior of neutron stars. So neutron stars and other astrophysical objects, they probe very dense matter. They nowadays also probe moderately hot matter if you look into neutron star mergers, for example. But the only experimentally accessible regime is the one that is accessible by heavy ion collision. So we start with ordinary nuclei, we collide and provide very high energy density, and we believe that you can move out into the phase diagram out here, which is mostly hot, but somewhat dense matter. So an experimental program to do this has actually been in existence since about the 1980s, but the first dedicated machine to do this was the RIC collider at Brookhaven National Laboratory. So this is an image of that. It's on Long Island near Brookhaven. And the large complex you see in the back is the relativistic heavy ion collider. It's about 3 miles around. And that started in 2000, colliding heavy ions of mostly gold, but also other nuclei, and in the meantime, also at other energies, but initially at 200 GeV per particle. So the two gold nuclei, they come in with Lorentz factors of about 200. So this is very ultra-relativistic heavy ion collisions. Now, it's a complicated program. It's been going on for 20 years now. So needless to say, there are many experimental results that I could not possibly cover in an hour. But if I had to summarize it in just one slide, then what was discovered is that at these very high energies, the basic theory of a relativistic heavy ion collision, which in principle is a very complicated event. It's a far off equilibrium, strongly interacting, strongly quantum. So it's a very complicated thing. It's described by a remarkably simple theory, and that's just ordinary relativistic fluid dynamics. So the sort of first order theory of everything is that everything flows, meaning everything is described by fluid dynamics. Okay, and one of the pieces of evidence for that is something that you see here, which is that in a typical collision, the two nuclei hit with some impact parameters. So this is what you see on the left is a computer simulation, but it's meant to be the nuclei are in the z direction and they're flying in the z direction. So this is the impact parameter plane, the xy plane. They don't hit perfectly center on. As a result, the initial energy deposition is somewhat deformed, roughly ellipsoidal in shape. And if an initial energy density like this is then evolved by fluid dynamics, what happens is that gradients in the initial energy density and pressure are translated into flow, into acceleration. The system explodes. But if the system is shorter in one direction and longer in the other, then you get more flow, more acceleration in the short direction. And that is called elliptic flow, the fact that the flow velocity in the final state is not the same in all directions. And this elliptic flow is characterized by these elliptic flow coefficients. Again, the one that describes the ellipsoidal deformation is called V2. The one that describes triangular deformation is called V3. And what is remarkable is that, so these are actual data points, these various objects. So this is elliptic, this is triangular, and so on. And what is remarkable here is that there is a theory that goes to all these data points, which is again relativistic fluid dynamics, And there's just one parameter in this whole fit, which is the specific viscosity per entropy density. So hydrodynamics converts this initial state geometry, including fluctuations of it, into flow. And this attenuation coefficient that is found is remarkably small. So it's a very nearly ideal fluid, indicating that the plasma is indeed kind of strongly coupled. So since then, 10 years after that, the energy frontier moved to the Large Hadron Collider. The Large Hadron Collider is, of course, primarily a high-energy physics experiment where people do proton-proton collisions to discover the Higgs and now look for other new particles. But a few weeks every year, the machine also operates as a heavy ion collider, colliding mostly lead atoms at energies that are significantly higher than the energies at RHIC. So initially at 2.7 TeV, and now that it's running at full energy at 5.5 TeV per lead nucleus. So the Lorentz contraction factor is now 5,000. There are several experiments along the LHC ring, but among them is at least one dedicated heavy ion experiment called ALICE. That's the one you see in the lower left-hand corner. This, by the way, is the standard sort of bird's eye view. So in the back, there's Lake Geneva. This here is France. This is Switzerland. And the beam goes back and forth between the two countries. It is also true, by the way, that in the meantime, there are two large particle physics experiments called CMS and ATLAS. And both of these detectors are also on when heavy ion running is taking place. They did not initially have large heavy ion groups, but they do so now. So the heavy ions have become an important component of the CERN program. Again, it's been running for 12 years now. Many data have been obtained. One of the more remarkable things that was already seen early on is that at the LHC, the energies are now so high that even in a proton-proton collision or a proton-nucleus collision, many of the phenomena that you see in heavy ion collisions at RHIC are also observed. So this is an example of this elliptic flow phenomenon. So this is again a plot of this elliptic flow coefficient V2 as a function of the transverse momenta of the particles that are coming out. The plot on the right is what this looks like in lead-lead at the LHC. So this elliptic deformation in the final flow velocities reaches something like 20%. But what is remarkable, that basically the same phenomenon with almost the same magnitude is already seen in proton lead and even in high multiplicity proton-proton, which is the thing you see on the left. So, the proton is only a Fermi across, but you can, at the LHC, at these energies, you can make a droplet of quark-gluon plasma that behaves like a fluid that is only the size of a single proton and then explodes. And again, the same kind of small viscosity is seen, implying that indeed the mean free path at these kinds of energies is smaller than the size of a single proton. It's pretty remarkable. Okay. So what is the next step, or what is currently going on? So what is currently going on, or has just been completed, is something called the RHIC beam energy scan, the BES phases 1 and 2. And what the goal is in these experiments is to go look for not just the properties of the quark-gluon plasma, but to go look for the phase transition itself, either by locating a critical point or by identifying a possible first-order phase transition. So the basic idea, and this is again a schematic phase diagram, what you see here on the left is again its temperature and baryon density. The basic idea is that we have some control over the initial conditions in a heavy ion collision by changing the initial energy and possibly changing the initial system size. And in particular, we think that at the very highest energies, the nuclei are so Lorentz contracted that the initial energy deposition is all produced particles. The nuclei just pass through each other and they leave behind some kind of fireball. And the fireball has essentially equal numbers of quarks and antiquarks. So the net baryon density is essentially zero at the highest energies. But at the somewhat lower energies, there is some stopping of the initial nuclei. And as a result, there's some net baryon excess, which are sort of remnant quarks of the initial participating nuclei. So the idea is that as you lower the energy, you actually move to the right into the regime of higher net baryon density in these heavy ion collisions. And so if this phase transition is just a crossover, and I'll explain in a minute why we think that is the case, it could be that as you move to the right, you will eventually get into the regime of first a critical endpoint and then a first order phase transition. And what we would like to do is look for evidence of that. And so what I want to do for the rest of the talk is first actually spend some time on why we think there is a crossover and why we think that there might be an endpoint and a first order phase transition, and then talk a little bit about the observables, and then finally talk a little bit about the theory that we're trying to construct that is intended to understand these phenomena. Okay. So I want to start, I'm sorry if this is somewhat too simple, I want to start very basic as to what is a phase of QCD and what is a phase transition. So QCD is a gauge theory. So the basic interactions are exchanges of massless gluons. And there are three basic phases of gauge theories, and the names are, they're usually known as the Coulomb phase, the Higgs phase, and the confinement phase. So in a Coulomb phase, if you have a gauge theory, the gauge theory has charges, either electrically charged electrons, for example, or color-charged quarks and gluons. And the basic interaction in a gauge theory is just a Coulomb interaction. So a Coulomb phase is simply a phase in which that is actually what is observed, that you see the microscopic interaction at long distances, you have a gas of charges and they interact via Coulomb interactions. In a Higgs phase, the basic gauge boson has acquired a mass by the Higgs mechanism, and as a result, the interaction is now very short range. So the interaction is decaying, and at long distances, you still have charges, but the interactions are weak. And finally, you have the Coulomb, you have a confinement phase. So in a confinement phase, the basic charged objects of the theory are confined into zero charge objects. And the long distance interaction between colored objects is a string potential, so that the color flux is forced into thin tubes. And the actual interaction that is observed is some kind of van der Waals interaction between color neutral objects. What is amusing is that in the standard model, we have three gauge theories, the U1 of electromagnetism, the SU2 of the weak interaction, and the SU3 of the strong interaction. And they make use of all three possibilities. So we believe that the QED sector is in a Coulomb phase, the SU2 sector is in the Higgs phase, and the SU3 sector is in a confinement phase, and that is what we observe. What is also amusing that we think that just QCD itself can explore all three possibilities, that in particular, if one studies QCD at very high temperature, we're in a Coulomb phase, that is called the quark-gluon plasma. If we have QCD at very high baryon density, then we believe that there's ultimately color superconductivity. Color superconductivity is characterized by a colored order parameter, a diquark condensate, that effectively acts like a Higgs field, and the gluon acquires a mass by the Higgs mechanism or the Meissner effect. And as a result, at very high baryon density, QCD is in the Higgs phase. And finally, of course, the ordinary phase that we observe at low temperature and low baryon density is a confined phase. Okay. Now, the thing about these phases of gauge theories is that these phases are qualitatively different, but they're not actually characterized by local gauge invariant order parameters. And as a result, the different phases of a gauge theory, they may or may not be divided by sharp phase transitions. You can typically go between these smoothly. So you can smoothly go, for example, between a Higgs phase and a confined phase. Okay. If you want to see rigorous sharp phase transitions where the correlation length actually diverges or some order parameter discontinuously jumps, then you need local gauge invariant order parameters. And in particular, you need global symmetries associated with these order parameters. Okay, so you need a local order parameter that transforms non-trivially under some symmetry. And then if that local order parameter acquires an expectation value, then there's broken symmetry and we can have sharp phase transitions. Okay. In QCD, there are two global symmetries that are a candidate for this kind of phenomenon. One is the conservation, one is the conservation of U1 charges like baryon number and electric charge. So these are just U1 symmetries where you transform by a phase. And the other one is the approximate chiral symmetry of QCD. So QCD has several flavors of quarks. They actually all have masses, but it's interesting to consider the limit in which this mass vanishes. In that limit, there is an exact flavor symmetry, which is called chiral symmetry, which is that you can make an independent rotation of the flavors of left-handed fermions and right-handed fermions. So you can relabel them by 3x3 matrices that I call left and right. So this symmetry is explicitly broken by the quark masses because the quark masses connect left and right-handed flavored quarks, but it's also spontaneously broken by a quark condensate. So we believe that there is an order parameter in the QCD vacuum. So there's a candidate for this kind of vector M, and this candidate is the chiral condensate psi bar psi, which connects left-handed fermions and right-handed fermions and selects out a direction in flavor space. So this is like some giant vector that acquires an expectation value in the QCD ground state. Okay. So chiral symmetry is then a transition that's connected with the global symmetry. Now, finally, it is also possible for theories to have transitions that are not directly related to a symmetry. In particular, first-order phase transitions can occur without a reason, if you wish. There may not be a particular symmetry related to that transition. And an example of that is just the phase diagram of water. So we have solid water, which is ice, we have liquid water, and we have water vapor. And the transition between the water vapor and the liquid water is a transition between two disordered phases. So there is no order parameter that is associated with the symmetry as you go from the water vapor to the water liquid. And indeed, as a result, the two phases are ultimately just continuously connected. So the first order phase transition has a critical endpoint, and you can just go around that endpoint and continuously connect the liquid and the vapor phases of water because they're both just disordered phases. Now, qualitatively, these two phases are quite different. So, for example, the pair correlation function in a liquid is very different from that of a gas, or the viscosity of a liquid is very different from that of a gas, but it's just some large jump in some quantity. Okay. So what are the signatures of that liquid gas endpoint in just ordinary water? Well, the main one I already mentioned, at that liquid gas endpoint, the correlation length diverges. And so you get fluctuations on all scales. In particular, you can get bubbles of the vapor inside the liquid, and near the very close to that phase transition, these bubbles come in all sizes. And as a result, they can efficiently scatter light of all possible wavelengths. And as a result, you get this phenomenon of critical opalescence. And in the vicinity of that endpoint, you also have an emergent order parameter, which you can just take to be the difference between the density of the gas to the density at the critical endpoint that can serve as some kind of order parameter. And you can write down an effective free energy functional for that order parameter, and its symmetries are just that of the Ising model. So this is a simple Ising kind of free energy functional, and you can get a first order and second order phase transitions where indeed just the shape of this potential changes. And in particular, near the critical endpoint, it has an emergent symmetry, which is just a symmetry on reflections between rho minus rho zero going from bigger than the density at the critical endpoint to smaller than the density. So in the Ising language, it's a Z2 symmetry where the magnetization changes sign. And as a result, precisely at the critical endpoint, you can get a second order phase transition characterized by the vanishing of this critical parameter R. And so there's a beautiful theory of that which describes how the correlation length diverges in the vicinity of the critical endpoint, and it diverges with some power law coefficient, which can be computed using various techniques like the epsilon expansion, but can of course also be measured in experiment. Okay. So now back to the real world. So what about QCD? Why do we think that there might be a critical endpoint like this? So in QCD, as I mentioned, there is kind of two candidates for possible phase transitions. One is confinement, so it's the phase transition associated with the gauge symmetry, and the other one is chiral symmetry, the phase transition associated with the global symmetry. Now, confinement in QCD is not a sharp symmetry or not a sharp phase transition because of the presence of light fermions. So, and intuitively, the way you can see this is that there's a string potential in a confined phase between two very heavy quarks. So the flux tube, the color gauge forces get confined into a flux tube. But in the presence of light fermions, the color flux tube can always break just by popping out QQ bar pairs, and a heavy quark antiquark system can always decay into a system of two heavy light mesons. And as a result, you never have sharp flux tubes at very long distances, and you don't have a sharp confining phase transition. In the case of almost massless fermions, you have a chiral symmetry breaking. So you have this order parameter that I already mentioned. It's not small, but we do have a finite quark mass. And as a result, it's not immediately clear that this is associated with the sharp phase transition. And so what is known from simulations of QCD, that it's likely that in the case of two light flavors, so just up and down in the chiral limit, this is a second order phase transition. As soon as you turn on a small quark mass, this will be smoothed out. In principle, in three flavor QCD, this eventually becomes a first order phase transition, which could potentially be robust to the introduction of small quark masses. But from numerical simulations on the lattice, we know that in the real world, where the strange quark mass is heavier than the up and down quarks, which are quite light, this transition is just a crossover. And the diagram you see on the right is an example of a numerical simulation that was published in Nature just a few years ago. And what you're supposed to see here is a susceptibility as a function of what is essentially temperature, but in the numerical simulation is the gauge coupling. And what you're supposed to see here, that the susceptibility shows a peak, so that's the indication of a phase transition, but this peak does not sharpen as the volume in a numerical simulation is increased. And that's a signature of the fact that the transition is just a smooth crossover. So the correlation length is not truly divergent, and the correlation length does not change as the volume is increased. So we believe that there's numerical evidence that in the real world, this chiral phase transition is a smooth crossover. There's also experimental evidence of that. So you can take these heavy ion collisions at Brookhaven, and we know that they have a very accurate description in terms of just fluid dynamics. Now, the way fluid dynamics is mostly done is that people just take the equation of state from numerical simulations of lattice QCD and try to describe the data. But you can try to reverse that procedure and just use a parametrized equation of state, many, many parameters, and try to extract these parameters of the equation of state by trying to fit data and spectra and flow and so on. And so what is shown on the left is sort of many, many possible equations of state, which are these blue curves, as a function of temperature, and here characterized by their speed of sound. So in a relativistic gas of massless quarks and gluons, ultimately the square of the speed of sound goes to a third. But if there is a phase transition, then near the phase transition, the matter would become very soft and the speed of sound would drop. Indeed, in a second order phase transition, or for a first order phase transition with some discontinuity, the speed of sound would eventually just drop to zero. And what you see on the right is these many, many equations of state now constrained by data through some Bayesian procedure. And what you see is that the data prefer that the speed of sound drops very dramatically as you approach a temperature on the order of 150 MeV or so. So the data actually favor a softening in the equation of state signaled by a lowering of the speed of sound, but they don't favor that the speed of sound goes all the way to zero. They just favor that it becomes small. So what that means is that the data indeed favor a crossover, so a softening of the speed of sound, but they don't favor a sharp phase transition where the speed of sound would go all the way to zero, okay? And that is done again by looking at many, many data. Okay, this is a result from Scott Pratt from a few years ago. Okay. So we then believe that the situation is that in this phase diagram, in the experiments at RHIC and LHC, the data favor that under the conditions at RHIC and LHC, there is a smooth crossover, but no sharp phase transition. So there's a softening in the speed of sound, but it doesn't go all the way to zero. Then as you go out to larger baryon chemical potentials or larger net baryon densities, there's roughly two possible scenarios. So this crossover transition, it could either become sharper and eventually become a first order phase transition where there's an actual discontinuity, or it could become softer. If you don't know anything, it's really just a 50-50 proposition. But in many of the models that we have, models of the QCD phase diagram and models of the QCD equation of state, these models do indeed suggest that the phase transition would steepen and it would eventually turn into a sharp first order phase transition, and that sharp first order phase transition would ultimately connect to a first order phase transition at low temperature and net baryon density, where you go from a liquid of hadrons to a liquid of quarks, okay? And so the question is, how would you see this? So again, there would be an order parameter that is analogous to the order parameter in the liquid gas transition. So an order parameter that could, for example, be just the difference in the net baryon density from the net baryon density at the transition, or the net entropy density minus the entropy density at the transition, or the chiral order parameter minus the chiral order parameter at the transition. And indeed, if you construct theories of this, you see that there's no reason that all of these cannot mix. So as a result, there's really just one order parameter, which is a mixture of all of the above in the vicinity of a potential QCD critical point. And if you construct free energies of as a function of that order parameter, you see that that free energy just has the form, again, of an ordinary Ising model, so that there's one linear combination of all of these, and that has a free energy density, which is just a free energy density of some kind of Ising model. And you would then predict that there is a critical endpoint, which is just of the form of the ordinary Ising model, so exhibits scaling, in particular scaling of the correlation length, which is just Ising scaling. And so this, again, a schematic model of this, so there could be a sharp first order phase transition, which you could just label just like an Ising model, that there would be a reduced temperature along that phase transition line and a reduced magnetic field. And what is amusing is that the thing we would in an Ising model call temperature is actually essentially parallel to what in QCD we would call chemical potential. And the thing that we would in an Ising model call the magnetic field is essentially proportional to what in QCD we would call the temperature. This red line, by the way, is actually experiment. It's a rough location of how the freeze out line evolves in actual experiments. So these are at the highest energies, and then these are at somewhat lower energies. This is the RIC regime, and this is eventually the CERN fixed target regime. So again, the idea is that you lower the beam energy, you explore this kind of freeze out line, and as a result, if there is a phase transition with a critical endpoint, there would be a magic energy where you're at freeze out, you're closest to this point. And the idea is that you would see remnants of critical behavior associated with this critical endpoint. So one thing indeed would just be to look for fluctuations, but what was recognized is that there are potential order parameters that are even more sensitive than just the correlation lengths. And these are higher moments of any of these possible order parameters. For example, higher moments of the baryon density, higher moments of the entropy density, or higher moments of the density of, say, the entropy density per baryon. So any of these, if you look at higher cumulants, would exhibit even stronger divergence than just order parameter fluctuations themselves. And what is particularly amusing is that once you go to higher moments, they don't even have to have a fixed sign, so they can diverge either in the positive direction or in the negative direction. And in particular, it's true in the vicinity of an Ising type phase transition that if you look at fourth moments of any kind of order parameters, so fourth moments, for example, of the net baryon density, you would predict this is an Ising type critical endpoint. This is an Ising first order phase transition, that on the first order side of the phase transition, this fourth order cumulant is positive, whereas on the crossover side of an Ising phase transition, it's negative, okay? So as a function of this Ising reduced temperature, it's positive on one side, negative on the other. And then your prediction would be that in actual heavy ion collisions, so the higher energy side would be this side. So you come from this direction, the order parameter, the fourth moment of the order parameter would first be negative, and then it would turn positive and show a strong divergence. So this is what one would hope to see, okay? What is amusing is that there is some indication from actual data from the first stage of the RIC beam energy scan that this is indeed what's happening. So what is plotted here is as a function of the beam energy. So this is the highest beam energies, which we believe are on the crossover side of the transition. These are lower beam energies, which could potentially be on the first order side of the transition. What is plotted here is a fourth order cumulant in units of the square of a second order cumulant. This is just a ratio where the volume of the system drops out. So that's experimentally particularly convenient. And you see some indication that at the high energy side, this is just random Gaussian fluctuations. So this particular ratio of a fourth order and second order cumulants is just 1. So everything looks Gaussian. And then as you go lower in energy, this particular ratio first becomes slightly negative. and then it possibly becomes positive. But you see that the error bars are relatively large. So it's hard to say that with any kind of confidence. However, so this is from the first stage of the beam energy scan. In the meantime, there's been additional data taking, and so there will be data that have already been taken, but they have not been fully analyzed yet, which A, will fill in this regime in smaller steps of the beam energy, and B, will have smaller error bars. So if indeed there's critical behavior, as is indicated by this kind of red line, which is actual easing criticality, then additional data would potentially show that with much higher confidence. Okay, so we currently have some indications. Data have been taken with higher accuracy, and we're looking forward to seeing what these data will show. Okay. Now, in the meantime, the theorists have not been idle. We also want to do more accurate theories of what precisely this looks like. So the question is, what is the dynamical theory near this critical point? The basic observation is that the logic of fluid dynamics still implies, but there's some important modifications. So we need an actual equation of state that includes the criticality, and we need to include actual stochastic behavior into the fluid dynamic description. And this implies in particular that we have to construct fluid dynamic theories that respect fluctuation dissipation relations. Okay. The simplest model for such a theory is just ordinary Brownian motion. So that's the simplest example of a theory that has stochastic behavior and hydrodynamic behavior. So Brownian particle is just a particle that is described by some momentum, and it satisfies a very simple dynamical equation. And the dynamical equation has two ingredients. One is a drag, so the particle is slowed down by interactions with the surrounding fluid, and the other one is noise. So the particle receives random kicks. These random kicks are completely uncorrelated, so they're described by white noise. So the correlation function of these random kicks, again, is completely uncorrelated. So it's just a delta function correlation. So the noise is just correlated with itself with some strength that is called kappa here. So this theory has in principle two parameters, the strengths of the kicks and the strengths of the drag. And the magic originally discovered by Einstein is that if the particle eventually equilibrates, so if the particle eventually has a dispersion in its momentum that is just governed by temperature, then it must be that the drag and the dissipation, the drag and the noise on average just balance. And that means that on average, their product is actually just determined by temperature. And that's called the Einstein or the fluctuation dissipation relation. The product of drag and the product of the noise is just given by temperature. And this ensures that the particle can eventually equilibrate. Okay. So the point is that we can write a similar theory also for a continuous order parameter of a critical mode in a hydrodynamic description. And that's a theory that's very analogous to the theory of this Brownian particle that I just wrote down. And in the case of fluid dynamics, this kind of theory is usually known as model H. So model H is just a name for the hydrodynamic description of a liquid gas phase transition that includes the diffusion of the order parameter and the noise. Model H is just a terminology that was invented many years ago for possible hydrodynamic descriptions of a critical order parameter, and they're just labeled by A, B, C, D. So the fact that water happens to have the name H is just a sort of accident of the labeling. Okay, so this theory, again, is still described by diffusive behavior, so that's analogous to drag of the Brownian particle. But now in the case of a fluid, there's also advection by a background fluid, and then there's noise, okay? The free energy functional in this case is again the one I wrote down earlier. We believe it's just an easing type functional where you have a quadratic sort of mass type parameter that in the vicinity of a critical point could potentially go to zero. And again, we have fluctuation dissipation relations. So there's noise here, but the strength of that noise is just delta correlation governed by the overall temperature. So this ensures that fluctuation dissipation relations are satisfied. Okay. What you see, by the way, on the right is an actual photograph of the density of a near critical fluid taken in an actual experiment with water that was done in microgravity so that one can very clearly see critical fluctuations. Okay. So people have done actual calculations with this kind of theory in infinite volume. In infinite volume, you can treat these sort of theories by methods that are very similar to just Feynman diagrammatic calculations in field theory, but the modes that are fluctuating are now just hydrodynamic modes. So there can be diffusive modes of the order parameter, there can be diffusive modes of the background fluid, and the relaxation of the order parameter is just described by the interaction of these various diffusive modes in the theory. So in particular, in the vicinity of a liquid-gas phase transition, the relaxation of the order parameter, which describes the relaxation of, say, the correlation length in the fluid, is indeed just described by the diffusive relaxation of order parameter modes coupled to the diffusive relaxation of the fluid itself. And the order parameter relaxation rate that one finds diverges as the third power of the correlation length. And in the language of critical dynamics, that's referred to as a dynamical critical exponent, which is just 3. So the relaxation rate of the order parameter scales as the third power of the correlation lengths in the fluid. So this is a beautiful theory, but in an actual heavy ion collision, the background itself is very dynamic. You don't have just a large box that's filled with a quark-gluon plasma and that you can very carefully study as you approach the critical point and look at the scaling with the correlation lengths. You have a very, very dynamic background, okay? And so what you can do theoretically is consider linearized stochastic dynamics about a non-trivial fluid background, which is the expanding fluid that we observe in a heavy ion collision. Okay, so it is still true that you can linearize about a background like that. And what you see is if you linearize the fluid dynamical equations of QCD, is that you still have propagating sound modes and you still have diffusive modes. And in particular, you have 3 kinds of diffusive modes. You have diffusion related to the order parameter, and you have diffusion related to the momentum of the fluid. These are called shear modes in the fluid. What you can imagine doing is look at noise averages of 2-point functions of these hydrodynamic modes. And again, you can define a kind of Wigner function for these fluid dynamic 2-point functions. And in the Wigner representation, these 2-point functions can be parametrized by the proper time as the fluid expands, by the location in the fluid, and by a Fourier wave number that corresponds to Fourier transforming in the relative coordinate of the 2-point function that you're looking at. And the diagonal moments, the diagonal components of this kind of Wigner function, you can interpret as a kind of phase space density of fluctuations in your fluid. So this is a possible variable for studying, or possible observable for studying these kind of sound and shear modes in the fluid. Okay. And so you can try to construct a theory for those, and the theory for those is some kind of relaxation equation for critical fluctuations. Oops, what did I just do? Okay, I accidentally stopped it. Let me get it back. Sorry for that. I think I fast forwarded too quickly. So you can study transits of possible critical points in QCD phase transitions. To be specific, I will consider as an order parameter, and that's a good approximation, I consider as an order parameter the entropy per particle in the fluid. That's one of these diffusive modes. And I can write down a relaxation equation that describes how fluctuations in this critical mode, again, characterized by this kind of Wigner function or phase space density, so they evolve as a function of time, and they evolve as a function of the wave number. And what they wish to do, or what they would do in an infinitely large fluid, is that these fluctuations of the order parameter would just relax to the fluctuations in an equilibrium fluid, the one you would see in an infinitely large box. And they do so by some relaxation rate that depends on the wave number of the fluid of this mode, okay? So there's an equation of motion, there's an equation as a function of time, which describes relaxation by some relaxation rate to the equilibrium behavior in an infinite fluid volume. In an infinite fluid volume, the 2-point functions, so these fluctuations of the order parameter, they would be truly divergent. So they would diverge, for example, in the case of entropy per baryon, they would diverge like the specific heat of that fluid. But at finite wave number or finite relaxation rate, the system is not truly divergent, okay? In a system like this, what happens is that there's some kind of emergent time scale. So in an infinite fluid, the correlation lengths would go all the way to infinity, but in a finite fluid, it does not go all the way to infinity. And in an infinite fluid, in a finite fluid, the relaxation rate is eventually limited by critical slowing down. So as a result, in an expanding fluid, the correlation lengths would like to become infinite, but there's not enough time to do so. So there's eventually some critical mode with the mode number that is comparable to the inverse correlation lengths that will fall out of equilibrium and not be able to evolve any further. And that emergent timescale we call the Kibble-Zurek timescale, and the associated correlation lengths, so the largest correlation lengths that you can actually achieve in a finite fluid that is undergoing expansion, is called the Kibble-Zurek length. And so if we try to estimate these times and length scales in an actual QCD fluid, what we realize is that the fluid cannot really achieve infinite correlation lengths. It achieves finite correlation lengths. And for typical parameters that are relevant to QCD fluids, that length is on the order of about 2 Fermi. Okay. So what I show here is an actual attempt to solve that numerically. So we have, again, this kind of 2-point function here of the 2-point function of a Gaussian fluctuation. Here, the Gaussian fluctuation is the entropy per baryon of the fluid. And it's shown as a function of wave number, and it's shown for different times. So initially, it's very close to equilibrium. And then as we approach the critical point, the fluctuations start to grow. The true equilibrium fluctuations would eventually diverge at 0 wave number, but this is a finite fluid. So it starts to fall behind the equilibrium fluctuations, and it falls behind further and further at low wave number. And then the fluid passes through the critical point. So this is near the critical point, and this is now later times. Now, if it were to stay in equilibrium, it would continue to track the equilibrium behavior, which would actually go away from the critical point. But the fluid has no memory. So there's some remembrance of the critical fluctuations that occurred earlier. And so as a result, there's some regime of wave numbers where the fluid still remembers, even though it now passed through the critical point, but it still remembers that there was a critical point earlier. So before the critical point, there's critical slowing down. The fluid wants to diverge, but the actual simulation lags behind. And as it passes the critical point, there's memory. So the equilibrium fluctuations are actually going back down, but now the fluid remembers that the critical order parameter diverged earlier. Okay. So what that means is that, number one, in principle, there is criticality, but in practice, the order parameter correlation length doesn't really go all the way to infinity. It can go to something like 1 or 2 Fermi. And you can also see that there really are critical fluctuations, but the critical enhancement is never infinite. The critical enhancement is really in practice something like a factor 2 or 3. So what these kinds of calculations show is that in an actual heavy ion collision, we can never expect to see the order parameter to actually diverge all the way to infinity. We can expect it to diverge by factors like 2 or 3. And we cannot expect it to see the divergence at all possible wave numbers. We can see divergences at wave numbers that correspond to the actual inverse correlation lengths that was reached, and those are numbers like 1 or 2 Fermi. So we see enhancements corresponding to momenta that are maybe 50 or 100 MeV. Okay. So, so to conclude, we believe that there is an opportunity. The opportunity is to discover a QCD critical endpoint by observing critical fluctuations in heavy ion collisions. And we believe that there's some intriguing hints present in the data from the first stage of the beam energy scan. We believe that in an actual heavy ion collision, you never see the sort of critical static divergence that you see in critical opalescence. And as a result, there is a challenge, which is to propagate the fluctuations of these conserved charges through actual relativistic fluid dynamics. Okay, so we have to describe initial state fluctuations, final state freeze out, and dynamics. The beam energy scan 2 data are currently being analyzed, and we hope to see them in the near future. As I mentioned, in practice, we think that the sort of enhancements that we're really looking for are really just factors of 2 or 3, and that we will see them by looking in the right regime in terms of critical wave numbers. But what is really also interesting that along the way is that we learned many interesting new things about fluid dynamics in the vicinity of a critical endpoint. Well, thank you so much, and I'm looking forward to your questions.
Thanks, Thomas. Sorry, there was a delay because this mic is not working. Can you hear us?
Yeah, this is better. There was previously some echo, but this is better.
Okay, sorry about that. But thanks very much for this very fascinating talk. And then we're open to questions now. So if you have questions, please ask. The audience in Zoom can unmute and ask, please. So just to begin, so I had a naive question. So when you mentioned that you look at this entropy per baryon as a kind of a order parameter. So, but in a heavy ion experiment, of course, there are viscosities. So this entropy is never conserved.
Yes.
So then, is there any ambiguity in taking this as the order parameter to look at the critical point, because they may be more diffusive, and then the information about the critical divergence may be more suppressed in these kind of observables?
Yeah, but that's precisely the point. So the what's the good slide to show? So indeed, the motion of this order parameter is dominated by diffusion, but that's exactly what you expect in the vicinity of a critical point, that the dominant motion of the order parameter is indeed diffusion. And that is indeed why it's nice to focus as an order parameter on something like the entropy per baryon, because its motion is actually purely diffusive, or at least approximately diffusive, all along, whereas, say, an energy density or a baryon density also has motion by just, say, sound modes or pressure modes, that the order parameter is indeed dominantly diffusive. Okay.
Okay. And also another related question I had is, you wrote about this, that there is no unique order parameter. It's near the critical point. It's a combination of your chiral condensate and the baryon number density. So if there is no unique order parameter, so when we discuss about these kind of modeling, does it cause any kind of ambiguity in the results, or is it?
Well, so in principle, there's sort of good news and bad news. So the fact that there's no unique order parameter, that it couples to the chiral field, that couples to the density, it couples to the energy density, it couples to the entropy density. In principle, the good news is that that means we should see critical fluctuations in all of these, because there's non-vanishing coupling to all of these observables. So we could actually look at any of them. The downside is that in some sense, we cannot predict necessarily which is the best one, because that's a sort of non-universal feature of a phase transition, what the coupling to these various modes are. So presumably some of them in practice are better than others, that we see in practice stronger coupling to the net baryon density, or stronger coupling to entropy fluctuations, or stronger coupling to chiral fluctuations, which you see in pions. So as a result, a priori, we don't know which is the best one. Okay, but presumably if there are critical fluctuations, they would be seen more strongly in one. So the good news is you see them in all of, you should see them in all of them. The bad news is we don't a priori know which is the best one. But in some ways, of course, the experiments, having been around for 20 years, they measure everything anyhow. So, so ultimately, if indeed there is a critical point, we would ultimately know whether the divergence is strongest in the chiral fluctuations, or strongest in net baryon fluctuations, or strongest in strangeness fluctuations, or charge fluctuations. So eventually, if there is one, we will know, but it's hard for us to predict.
Okay. So, but in the lattice, we never measured this fluctuations of the chiral condensate.
Yeah. So so if indeed one could do lattice, do I show any lattice results? Not really. So on the lattice, of course, you can do reliable calculations along the temperature axis at 0 chemical potential. And you can measure things like this chiral susceptibility, which is shown here. Okay. Now, this yellow band, by the way, is lattice simulation. So you can try to do these Taylor expansions and you get some idea about the curvature of the phase transition line. But the lattice, of course, sees no indication of this sharpening that would correspond to an actual first order phase transition and associated endpoint. Now, if they could do simulations, they could, of course, again, tell us what the critical mode truly is, because on the lattice, they could just measure all of these. They could measure fluctuations of the chiral susceptibility, of the baryon susceptibility, of the electric charge susceptibility, of the strangeness susceptibility. They could measure all of the above, and as a result, they would be able again to tell us what the critical modes are and how these lines are actually oriented and so on. But again, that may not, at least in the foreseeable future, that they may not be able to tell us. It could be that this critical point, even if it exists, is so far removed from the temperature line that the lattice just cannot tell us what the coupling to these various modes is.
Yeah. Yeah, thanks. Are there any questions? Yeah.
A very basic question. In your very earlier slides, I think slide number 2 or 3, you showed that so you were talking about every phase QCD theory can exhibit. For example, at high temperature, it will be like Coulombic phase, and then like at low temperature, it is confined. But you said it has high mu chemical potential, it will behave as Higgs phase. So can you please elaborate? I couldn't understand that.
Yeah, so this is something which I spent many years of my life on, but didn't really talk about very much here. It's this idea that at very large net baryon density, QCD could have a color superconducting phase. That is not a phase that you can easily probe in heavy ion collisions, but it is a phase that could be relevant to the behavior of neutron stars. And the idea is very simple, that in QCD, you could have a phase which is analogous to Cooper pairing among electrons. So Cooper pairing among electrons is that in a metal, you have a phase where electrons pair up, a spin up electron and a spin down electron pairs up, and they form a boson, and the boson can eventually condense. That's a condensate of charged particles, because the net charge of an electron pair is 2 times E. And so you have a condensate of charged particles. In QCD, it's even easier to form such a condensate because the main interaction between 2 electrons is Coulomb repulsion. So electrons, in some sense, do not want to form Cooper pairs. It's a very subtle mechanism that allows Cooper pairs to form. But in QCD, 2 quarks of opposite, of different color, say red and blue quarks, actually attract by color-gluon exchange. So in QCD, it's extremely natural that you would form Cooper pairs of quarks, and that these Cooper pairs of quarks, which are bosons, can just condense. And so if you have a condensate of Cooper pairs made of quarks, you have a condensate of colored objects. And that condensate of colored objects is like a colored Higgs field. It's a scalar field that carries a joint color. And so that would lead to a Meissner effect, and other gluons would now just acquire a mass by the Higgs effect. Okay, so you would have a phase in which you have a condensate of colored quarks, and gluons are effectively massive by the Meissner effect. So this is a phase that we would usually refer to as a color superconductor. And in terms of this kind of general classification of phases, we would view it as a Higgs phase. So this kind of Higgs condensate that is somewhat indicated by the wavy line here, what it would be microscopically is not a fundamental scalar field, as in the Higgs effect in the standard model, but a composite Higgs field made of quark-Cooper pairs.
Okay, thank you.
Does that make sense?
Yes, I could follow. Thank you.
Hello, sir. So what do you mean by local order parameter? I do not understand that. Can you just elaborate?
Yeah, so a local order parameter is just any object of this type, that there's some object, which I hear generically called M, which is a local field, meaning it's just a function of X. It can be defined at any point in space, and it's gauge invariant, meaning it's an observable. It carries no net color. And what people observed many years ago is that even though we can qualitatively talk about these various phases of gauge theory, we sort of know it when we see it, there's no local order parameter that tells you whether you're in a Coulomb phase, a Higgs phase, or a confinement phase. And at a sort of hand-waving level, you can see this because the difference between a Coulomb phase and a confinement phase is the behavior of the potential between two charged objects. So what you need to know in order to know whether you're in a Coulomb phase or a confinement phase is what is the potential between two charges. And in a Coulomb phase, it's 1 over r, and in a confinement phase, it's linear in r. But a potential is not a local gauge invariant object. It's you need to put down two charges and separate them by some distance. And so this potential is not defined locally, it's some bilocal order parameter. We place one quark in one position and one quark in another position, and then we measure the potential. And so if the distinction between two phases is given by a non-local object, then this kind of Landau logic of classifying phases by local order parameters does not immediately apply. So we cannot be sure that a transition is a thermodynamic phase transition. The phases are certainly qualitatively different, but they need not be connected by sharp phase transitions. So the free energy need not diverge, for example, because there's no local object that distinguishes them. And the same applies to this kind of Higgs phase as well. So a Higgs phase, loosely speaking, is characterized by an expectation value for a Higgs field that can either be a microscopic field like the Higgs field in the standard model, or a composite field like the diquark condensate or the Cooper pairs in a superconductor. But the Higgs field is a color charged or SU2 charged object. So strictly speaking, in a gauge theory, it depends on the gauge. So when you say that the Higgs field acquired an expectation value, that's formally speaking a very subtle statement, because a Higgs field is not a gauge invariant field. And so when you say that it acquired an expectation value, you talk about a statement in some theoretical description where you somehow fix the gauge. And in some other gauge, it could potentially have a different expectation value. So again, it's not immediately clear. It may be possible, but it's not required that you can write down some kind of free energy functional as a function of the Higgs field, because the Higgs field itself is not even gauge invariant. So as a result, there could be a sharp phase transition between a Higgs and a confined phase, but there need not be, in the same way that there has to be a sharp phase transition between a magnetized object and a non-magnetized one. So this analogy is not exact because, again, the magnetization is a gauge invariant order parameter, which you can definitely measure, but the Higgs field is not a gauge invariant order parameter. And as a result, you cannot directly measure it. You can only measure its square.
Okay, sir, thank you.
Hello. So sorry, this is in continuation of what I asked before about this like confinement Higgs phase, QQ bar pair. You said.
Yes, go ahead.
No. So I had this question that suppose we are at suppose we are at high temperatures,
Yes.
but
Yeah. So yeah, just
so we
continue.
are
I think
yeah, sorry. So we are at high temperatures, but also we have very high chemical potential. In that
yes,
case, also we can form these Cooper pairs, or they
yes.
will keep on transferring to the like QQ, like not the confined system, because this also looks like confinement, right?
So yeah, two comments. Number one, so here I don't show this very sharply, but so what this phase diagram suggests is that we somehow believe that these Cooper pairs are condensed at low temperature and they're not condensed at high temperature. And at some level, this is just empirical observation that all these both condensed phases that we know in nature liquid helium, electronic superconductors, condensed ultra-cold gases. These are systems that are bose-condensed at low temperature, but not at high temperature. And in some sense, that's easy to understand because a Bose-condensate is some kind of phase-coherent state. As you go to higher temperatures, you add more and more fluctuations to the system. So at some point, there is a critical phase transition where Bose-condensation disappears, and these Q-Q pairs or electron-electron pairs are no longer condensed. And indeed, if one tries to estimate that in QCD, we find that the energy gap associated with Cooper pairs is something like 100 MeV or so. So as soon as you get to temperatures that are on the same order, so temperatures on the order of 100 MeV or so, we believe that this kind of phase coherence associated with Cooper pairs is somehow lost. And indeed, you don't get condensed Cooper pairs, you break the Cooper pairs, and they just, again, form a gas of quarks and gluons. So that you have a quark-gluon plasma, and what happens at very high baryon density is just that the quark-gluon plasma is enriched in net quarks. So it's a quark-gluon plasma, but one that has more quarks than anti-quarks, but there's no phase coherence associated with Cooper pairs of quarks. The sense, by the way, in which this Higgs phase is sort of quasi-confined is simply the sense in that there are, in principle, excitations that are individual quarks, but there's an energy gap associated with them. So the Higgs phase is somehow quasi-confined in the sense that it actually takes a lot of energy to make a quark because there's an energy gap associated with them. Whereas in a Coulomb phase, there's no energy gap associated with individual quarks. So in a confined phase, this energy gap is, at least in principle, infinitely large, although in practice, the string always breaks. So in a theory in which the string can break, there's not an infinite energy gap associated with quarks, but a finite one. And in a Higgs phase, there's also a finite energy gap associated with quarks. So that's the sense in which a Higgs phase is at least potentially continuously connected to a confinement phase. Any confined phase in which the energy gap is not infinite but finite because of string breaking, say, can in principle be continuously connected to a Higgs phase because it has a finite energy gap for charged excitations.
Okay, thank you very much.
Thomas, I had a naive question. So when we usually show the QCD phase diagram, we don't include the effects of SU2 electroweak, and so will the diagram change a bit if we consider SU2 the left sector of the?
Yeah. So in principle, indeed, there is a complicated phase diagram because in QCD you have kind of three conserved charges within the context of QCD, which are baryon number, strangeness, and electric charge. And in principle, you can consider a phase diagram that has two extra directions. And so, so one of the reasons why I don't show it, because it's too complicated to plot. So it's somehow hard to visualize these two extra axes. The one that's most relevant in nature, so strangeness, of course, in the standard model is ultimately not conserved. So strange quarks can always decay. The only thing that can happen in a heavy ion collision is that there may not be enough time. But electric charge is actually truly conserved. So in some ways, the most important axis to add is the direction of electric charge. Now, in nature, if you make a large object, electric charge ultimately always has to be neutralized, because if you have an object with large net electric charge, it has a large Coulomb energy, and you cannot ultimately make that. So a neutron star ultimately has to be electrically neutral, because if it had a large net electric charge. Now, what happens in a neutron star is, of course, that you can have electric charge in hadronic matter that's balanced by electrons. And we believe that that actually does happen, that in a neutron star, you optimize energy by having some electric charge in electrons balanced by electric charge in protons and neutrons. So we believe that a neutron star actually goes off in that direction, that there's some net electric charge in isospin balanced by electrons. And that's indeed a very important phenomenon. And figuring out exactly how the QCD phase diagram is modified in the isospin direction is very relevant to neutron stars. And of course, there are numerical simulations that explore that, and it's quite relevant for the actual equation of state in neutron star matter. And indeed, neutron stars are called neutron stars because we think they're enriched in neutrons.
Yeah. Will it affect the critical endpoint here?
Yeah, so that's, of course, a very good question. So if this critical endpoint exists, then how does it evolve in the isospin direction? And it will certainly evolve. And we don't have, from either the, within models, you can study that, it'll certainly move, but we don't have much rigorous information in that direction.
Okay. Yeah,
it'll move, indeed. It'll move. It'll indeed move both as a function of isospin and as a function of strangeness. It'll certainly move.
Okay. But there are also no model studies very well done on this.
No, there actually are many model studies. I mean, if you look at people who played around with, quark meson models or random matrix models, it's something that has been studied in models.
Okay. Yeah, thanks. People in the Zoom audience, do you have any questions? You can please unmute and ask. Okay, I don't see any. Oh, sorry. Yeah, please go ahead.
Hi. So can you go to the Outlook slide? There's this comment, there's this challenge, propagation of fluctuation of conserved charge. Can you explain that a little?
Yeah, so what I was saying roughly is the following, that in a perfect world, the experimentalist would just measure one of these fluctuation observables, and they would see, some kind of dramatic variation as the one like I indicated here. Let me see where that is. Okay. So you would do some experiment like this, and you could hope that the data would eventually just show a very dramatic non-monotonic variation of this type, which would be reflective of critical fluctuations that occur on the freeze-out surface, but that are actually close to a critical point in the phase diagram. But in reality, it may not look as pretty as this, because the heavy ion collision itself is a very dynamic system. There's critical slowing down, there's memory effects, the correlation function cannot truly diverge. And so as a result, it may not look as dramatic as it does on this cartoon. And then there would be a challenge, which is to understand that theoretically, why certain observables would show some non-monotonic variation, but not a real divergence. And so this we would model as some non-equilibrium behavior in the vicinity of this critical point. We would ascribe it to indeed these phenomena like critical slowing down, memory effects, Kibble-Zurek scaling, and so on. So one challenge is to simply understand exactly how much of a divergence can you actually get in a dynamic system like a heavy ion collision. The other challenge is that in an actual detector, you cannot really observe something like critical fluctuations in the entropy per baryon. all you actually measure in a detector is particles. And so one of the theoretical challenges is to understand how fluctuations in some abstract order parameter translate into fluctuations of actual particles. And in particular, we cannot even measure something like the conserved baryon number. All we can measure is protons, but we cannot see neutrons, for example, or we don't see all the hyperons. And so as a result, all of these theoretical order parameters like baryon number or electric charge, we cannot directly measure them. We can only measure some particles, but not others. And so if you describe experiment, you have to somehow understand how fluctuations in some abstract order parameter are actually translated into fluctuations in things that you can measure, like protons and pions and kaons and so on. And that's a challenge that I actually haven't really talked about in this talk, but that people are studying. How do you get from fluctuations in an order parameter to fluctuations in actual particles in your detector?
Thanks.
Hi. So you just told that in crossover that we don't have a volume dependence of that susceptibility. So is that true? That means if we have a first order transition, then this kind of order parameter or fluctuation has a system size dependence. Can one say that?
Oh my. So actual lattice experts would immediately know the answer, but I don't. So if you look in a sort of typical book on order parameters, you will see, so at a second order phase transition, it's supposed to diverge. And if you're away from a phase transition, it would be volume independent. There is a signature of first order phase transitions, which I can now not recall, but if you have a lattice expert.
I really wanted to ask this because if that happens, then in our system, like proton-proton collision and gold-gold collision, there should be some kind of difference between this first-order transition region and crossover transition region. So
yeah, so that's an important question, which I now don't have a good answer to, but it's something that I could certainly point you to some literature.
Okay. Thank you.
Okay. I see no further questions in the Zoom and no further questions here. Oh, there's a question. Sorry. Yeah.
So hello, sir. So are the composite object like you just told the Cooper pairs only with two is available, or for more than two is also available? I mean,
yeah, so in principle, condensation can occur of any kind of bosonic object. So the sorts of objects that could condense pairs and bound states of 4, bound states of 6, and so on. So that, again, is in principle already true for ordinary electronic systems. So instead of Cooper pairing in an ordinary electronic superconductor, in principle, it could be that you have bound states of 4 electrons. Now, I think it's already intuitively clear that typically these are more difficult to make. So we don't know of any electronic superconductors that are based on condensation of 4 electrons. Now, in QCD, the situation is less obvious. So in weak coupling, we can, if there's just a weak attraction between the quarks by one gluon exchange, we can see that you get Cooper pairing of quark pairs, but you don't get condensation of 4 quark objects, because roughly speaking, phase space for that is just somehow suppressed if you analyze it in weak coupling. They're harder to make. But in QCD, of course, we do know that in general, there are all sorts of bosonic bound states. You know, there are deuterons and there are helium-4s and God knows what. So in principle, in QCD, it is perfectly plausible that in strong coupling, there could be condensation of more complicated objects. And so roughly speaking, in this kind of phase diagram, at extremely large baryon density, we would expect on the grounds of perturbative calculations that you get Cooper pairing, so that there's a condensate of quark pairs. And we know that at very low density, the answer is ordinary nuclei. But in between, in principle, there's all sorts of possibility. There could be condensation of neutron pairs, which we think really does happen. There could be condensation of deuterons. There could be condensation of helium-4. There could be, at these moderate densities, there could be condensation of objects that are 4-quark bound states. So in principle, in QCD, because it's strongly coupled, any bosonic object could, in principle, condense.
Thank you.
Sir, this is a very basic question. This QQ bar pairs, which doesn't have the charge, and this QQ, which is having the charge and it's condensate, this produces this kind of critical point and phase transition behavior.
Yeah.
And I just want, it's a very basic, I mean, why there is no such kind of phase transition in this QQ bar systems? Just like this E plus E minus and E minus E minus, this Cooper pair things, and here there is no.
Yeah, so in QCD, so I haven't really talked about this in detail here, but indeed, in principle, you have these sort of two order parameters. One is Q bar Q or psi bar psi, and the other one is QQ or psi psi. And so the difference that I mentioned is that psi bar psi is a color neutral object. So psi bar psi is a color neutral object. So it can serve as an ordinary order parameter in the sense of Landau, and it can be associated with sharp phase transitions. Whereas QQ is an object that's color charged, so it does not serve as an ordinary order parameter in the sense of Landau. So psi bar psi chiral symmetry breaking is a local order parameter and can have real phase transitions. The only issue in QCD is that there already is, in some sense, a psi bar psi object already in the Hamiltonian, because that's what the mass parameter looks like. So QCD has a mass parameter, and that means that already in the Hamiltonian, there's a term that's m times psi bar psi, which acts like an external field for the order parameter associated with chiral symmetry. So in QCD, there always is a small psi bar psi just associated with the masses. And then there could be a large psi bar psi associated with chiral phase transitions. But because the small psi bar psi already exists, the transition in the large psi bar psi does not have to be sharp. It could be smooth. And that has to be carefully studied as a function of the number of quarks and of their masses. And so this is what lattice simulations can do extremely well. And so this produces this sort of plot, which shows that in the real world, so this is meant to be for realistic quark masses, this does not actually diverge. It's just a smooth crossover, which is roughly in the high temperature phase, psi bar psi, driven just by the quark masses, and in the low temperature phase, psi bar psi, driven by spontaneous symmetry breaking. However, if, in artificial worlds, you can take the quark masses all the way to 0, and then you would get sharp phase transitions. In the phase of Cooper pairing, this is a complicated question. So, and this is kind of why there is a sort of question mark here. So in this regime, what you can have is a phase transition from spontaneous breaking of chiral symmetry, meaning Cooper pairing of quarks and antiquarks, to Cooper pairing of quarks. This could be a sharp phase transition, a first order phase transition, we just don't know, or it could be a smooth crossover where you change continuously from pairing of quarks and antiquarks to pairing of quarks. And in this regime, all we have is observation of neutron stars, so it's very hard to tell empirically what happens. and we don't have ladder simulations. But it's a very important and very interesting question, what the phase transition between Cooper pairing of quarks and antiquarks and Cooper pairing of quarks, what that ultimately looks like. So in models, you can study it, but in nature, we don't quite know.
Okay, I see no further questions. So thanks, Thomas. It is indeed a very great privilege for us that you agreed to kindly give this distinguished lecture as a part of our 68th year celebration, and also for patiently answering all the questions. And it was a real pleasure, and I would request that next time when you come to India, do visit us, and we'll be grateful to see you in person and interact with you.
I certainly hope to do so. And again, thank you very much for having me.
Thank you.
Thank you.
Bye-bye.
Thanks.
So we will end the session now, and okay.